Hello again, it's Mrs. Harding. I'm here to take you through the final lesson of Chapter 1, Lesson 1.3b. The main highlights of what we're going to hit today, we're going to calculate and interpret measures of variability. We talked about IQR in the last lesson. Today we're going to talk about standard deviation. We're going to make and interpret a box plot. And we're going to use box plots and numerical summaries to compare the distributions of quantitative data. So let's jump right in and talk about something called a modified box plot. There at the very beginning of the lesson, we're referencing something called the five-number summary. The five-number summary, I'm going to switch screens here for just a second. There we go. The five-number summary is made up of these five numbers: the minimum, Q1, the median, Q3, and the maximum. These are called the five-number summary, and the five-number summary is what we use to build a modified box plot. This is another display of quantitative data. It does not show you the individual data values from the set. It shows you just a snapshot of the important points that you want to pay attention to. So in this data set, it says below are the weights of the 2009 Dallas Cowboys offensive linemen. Now, if we go through and find these numbers, first let's find the median. The median is here in the middle, 317.5. The middle of the lower half is Q1, it's 311. The middle of the upper half is Q3, that's 326. The minimum number is here, the maximum number is there. So you see the list: 307, 311, 317.5, 326, 356. This is called the five-number summary. From the five-number summary, you can get the IQR, which is Q3 minus Q1, so that is 15. So then what does a box plot look like, and what can you figure out from the box plot? Well, I'm going to help you go through the steps to create the picture that you're looking at. The first step: above the scale, draw a rectangle that extends from Q1 to Q3 and divide the box into two parts with a segment above the median. So we have the median at 317.5. Q1 is 311. Q3 is 326. This is the first thing that was drawn in this picture, is that box in the middle. That is the IQR. That is the middle 50% of the data. The middle 50% of weights is from 311 to 326. Find the smallest value that is not considered an outlier and the largest value that's not considered an outlier. All right, well, then that means that we have to go back and determine if there are any outliers in the set. And you can see the work at the top there. We have Q1 minus 1.5 times IQR is 288.5. And then the upper cutoff, 326 plus 1.5 times 15 is 348.5. So any numbers less than 288.5 or greater than 348.5 would be considered an outlier. And in this case, we do have an outlier. 356 is larger than the upper cutoff, so that is considered an outlier. So if we go back to this, find the smallest value that is not considered an outlier. Well, we don't have any lower end outliers, so this is out to the minimum, the minimum of 307. Find the largest value that is not considered an outlier. Well, 356, the maximum number in the list, is an outlier. The next biggest one, 338, is not an outlier. So 338 is the largest number in the data set that is not considered an outlier. Put an asterisk above any outliers. So that right there is your modified box plot. What can you tell from the graph? If all I was given was this graph, I could give you the median, which is the measure of center. I could give you the Q1, Q3 and tell you what the IQR is. I could tell you if there were any outliers. I can even talk about any kind of skewness from the graph. If you look at this, you can see because of the outlier, because of the longer bar here, this graph is skewed to the right. There are a handful of very large values in this data set. Okay, so keeping in mind that IQR is most often paired with median, and that median is used when you have a data set that is skewed or has outliers, you are using IQR and median together as the measures of center and spread in the scenario where your distribution is skewed or it has an outlier. So what do you use as your measure of variability in a symmetric data set? Well, remember I told you that we had used range in the past, mostly because that's what you were familiar with when it came to variability. But we're going to add to our list of measures of variability the idea of standard deviation. And many of you may have heard of standard deviation before, but this is the measure of spread that is typically paired with the mean. The data set that we're going to look at to talk about standard deviation is here in the table. This is the average monthly temperatures for Raleigh, North Carolina and San Francisco, California. Below is a dot plot of each of these. It does have the median, the mean marked on them both on the screen for you. Remember, X bar is the mean. But I'm going to show you a couple of things on your calculator today too, so you can quickly get this information. On the next page, it asks you which city appears to have greater variability in average monthly temperature. So take a look at those two dot plots. Look at the scale that they're plotted on. Which of those would you say has the greater variability? Hopefully you said Raleigh. I want you to also consider this idea. Estimate the average distance from the mean for the temperatures in each city. So what does that mean? Well, let's look at San Francisco down here. Here's where the mean is. You can see that there are some numbers in the set that are quite far from the mean. These out here at 49 and 65, they're quite far from that mean. But then there's another, like 58 or 56, that are quite close to the mean. What would you say is the average distance that a data value is from the mean in that distribution? On the next page, I'd like you to write down your estimate for Raleigh and for San Francisco. You can see what we estimated, about 10, about 6. Well, this concept of the average distance from the mean is something called standard deviation. You can get standard deviation from your calculator. The calculation of it can be a little bit tedious. So for right now, we're going to go to our calculator and do something called one variable stats. I'm going to show you everything that's in this handy little place in your calculator. So if you need to pause to enter the data, go ahead and do that. I have my data already entered. Those are all of the temperatures. Oops, and even as I'm sitting here, I see one that I did not enter accurately. It looks like that was supposed to be 78 right here. Let me fix that before we move on. 78. There we go. Okay, so to get all the information about these, you can go to a place called One Variable Stats. One Variable Stats is, I'm going to close out of this screen, hit the Stat button, arrow over to the Calc menu, and then you see One Variable Stats right there. I'm going to tell you everything that you're going to see in this list. I'm going to do list 1, which is just Raleigh. And here's what I can find. I see the mean temperature is 59.25. It also has the sum of all the values, the sum of all them squared. These are not numbers that we're really going to use, but you can see here S sub x. This is the standard deviation. So the standard deviation for Raleigh is 14.2. The other things in the list, it tells you what n is if you didn't know. And actually, if you scroll down, you're going to see the 5-number summary right there. Minimum 39, Q1, median Q3, and maximum. So this is a screen that you can use to sort of be a little bit more efficient with your work. If you want to take a moment here and figure out the standard deviation for San Francisco also, go ahead and do that. And the standard deviation for San Francisco is 5.8. So you can see that Raleigh has the larger standard deviation and has greater variability. I just want to make another statement about this. I know that with my classes I talked about the importance or lack of importance maybe of the measurement of range. Moving forward, when you're describing the variability of a graph, it's more important for you to use either IQR or standard deviation, depending on the shape of the graph, and less important for you to state range. Range sometimes is the only measurement that we're able to determine in a given problem, in which case that's okay. But we're going to try to focus more on IQR and standard deviation as measures of variability. I also want to go back and talk about a couple of formulas. Down here at the bottom, there are some formulas. This is what they're going to look like on the AP formula sheet. So you should become a little bit familiar with them. This is the mean. We talked about that one already. This is the standard deviation here. Now we discussed just in general how to find standard deviation, but specifically you're adding up the distances of all of the values from the mean, squaring it. I apologize, I just said that backwards. You're going to find the distance from the mean, square it, and then add them all up. What's the purpose of squaring? The purpose of squaring is because you could have some negative distances. So we're going to sum them all up. We're going to divide by n minus 1. We can get into this a little bit more later, why it's n minus 1 and why it's not n. It's related to sampling. But then take the square root, and that will give you the standard deviation. So you should just be familiar with what these definitions look like. Variance is simply the square of standard deviation. So here inside the square root is considered the variance. So sometimes you'll hear standard deviation referred to as the square root of variance. All right, let's take a look at a new data set. Here we're going to come back and look at 3 different types of cars and their highway miles per gallon. The 3 types that you have are the upscale, the sports cars, and the small size cars. The tables underneath this show you an IQR and a standard deviation for each of these distributions. Without doing any calculations, I would like you to try to determine which table represents which type of car. So go ahead and pause and put down your answers. All right, compare your answers with what we have up here on the screen. You should have noticed from those distributions that the upscale cars were most tightly clustered. They have the smallest variability, therefore the smallest IQR, the smallest standard deviation. The next most tightly clustered dot plot is the small cars. This section of the small cars might have about the same variability as the sports cars, but the sports cars have a large outlier, which is going to give it a larger standard deviation. Take a look at the next page. We're going to compare IQR and standard deviation as measures of variability in these 2 different data sets. It says below are weekly salaries of 2 fast food restaurants. Go ahead and enter these into your calculator. Salaries for McTofu and salaries for Moose Burger. And we're going to take a look at the IQR and the standard deviations for both sets. So take a moment, use your calculator, figure out what those numbers are. This will give you some practice with the one variable stats. And then make sure that you were able to get the numbers that we have on the screen. And it says, why is there such a large difference in the standard deviations of the 2 sets, but not the IQRs? Well, looking back at this data set, look at McTofu. The spread here from 100 up to 360. This 360 up here is much larger than the other values in the data set. This would be an outlier, as opposed to Moose Burger, where they're all relatively close to each other. 110 is the smallest, 160 is the largest. This outlier up here impacts the standard deviation, but not the IQR. The IQR, remember, is just telling you how wide the middle 50% is, the middle half of the data. So the IQR is not as affected by an outlier. The standard deviation, however, is very much impacted by an outlier. So this is another reason that when you're describing the variability for a distribution, if the distribution is skewed or it has an outlier, you want to use median and IQR. Those two measurements are resistant to the effects of an outlier. However, the mean and the standard deviation can be very much impacted by an outlier. Take a look at the example here. Table below shows the home run counts for Barry Bonds over 16 seasons, not in any particular order. It says, describe the distribution in context. Well, I would like you to put these numbers in order, and I want you to verify what you see. Measures of center, measures of variability. Tell me what the shape is. Are there any outliers? And it says in there, once you get it all graphed out, you should see something that is fairly symmetric. However, because of an outlier at 73, we are still going to use the median and the IQR as measures of center and variability. So the distribution of home run counts for Barry Bonds, that's your context, over 16 seasons is symmetric, it's your shape, with a median of 34, that's your center, and an IQR of 16, that's your variability, with an outlier at 73. So in summary, here at the bottom, a couple of things just to keep in mind. If the shape of the distribution is skewed or it has outliers, you're going to report the median and the IQR. If the shape is symmetric and there are no outliers, then you're going to use mean and standard deviation. If there are any clear outliers in the data and you're using the mean and standard deviation for measures of center and spread, you would probably report these values with and without the outliers, since the mean and standard deviation are not resistant to outliers. That's saying that if you're going to use the mean and the standard deviation, even with an outlier in the set, you might want to discuss the center with and without that outlier. So what would the center be with it? What would the center be without it? You're always, always, always going to pair median with IQR and mean with standard deviation. There's never going to be a time where you're going to report the mean with the IQR or the median with the standard deviation. All right, then the last thing that we're going to do today is I'm going to pause and I'm going to let you complete the last page for the check your understanding. Okay, so hopefully you created a box plot of the two data lists to compare, and it becomes pretty clear that the females are likely the ones that are texting more often. And in looking at the modified box plot, half of the females texted more than 75% of the males. So if you look at this from the median on, half of the females here texted more frequently than the bottom 75% of the males. So we're going to use that as our reasoning for saying that the females text more. That brings us to the end of Chapter 3. If you have any questions, as always, please let us know.